Welcome to Unit 3, Lesson 2. And today we are going to take what we learned about finding probabilities of simple events and use that knowledge and some new knowledge to find the probability of compound events. Okay, the first thing we're going to talk about is independent events. The occurrence or non-occurrence of one event does not change the probability that the other event will occur if the two events are independent. So that is a condition for the rule that we're going to learn. So an example of that would be tossing a coin and rolling a die. If you toss a coin and it lands on heads, the probability of rolling a 4 is still 1/6. It's a probability, if the coin lands on tails, then the probability of rolling a 4 is still 1/6. It does not, the probability you get from rolling a die does not change given the outcome of the coin toss. So if events A and B are independent, then the probability that A and B occur is found simply by doing the probability of A times the probability of B. If events are not independent, which is most of the time, the fact that one occurs affects the probability of the other. PA given B equals the probability that event A occurs, assuming that B has already occurred, and the probability of A given B is written P and then parentheses A and then a little line B close parentheses, and it's read the probability of A given B. So the general population rule for any events, it actually turns out that this works for independent events too, is the probability of A and B is equal to probability of A times the probability of B given A, or you can do the probability of B times the probability of A given B. So, in summary, you've got one rule for independent events, so you have to make sure that your events are independent, and then you have rules for any events at all. Okay, so when choosing two cards from two separate decks, okay, so I have two decks of just standard cards, and I want to know the probability of getting 2 5s. Well, since we're pulling the probability, the cards from the two separate decks, the probability of drawing a 5 from the first deck is 4 out of 52 because there's 4 5s out of a set of 52 cards. And then from the second deck, it is still 4 out of 52. And on these, again, you don't necessarily have to reduce. I tend to just because it keeps the numbers smaller and it keeps me from having to use a calculator. You do want to express these as fractions because there's a lot of rounding that would have to happen if you do decimals. So 4 50-seconds divided by 4 50-seconds is 1 over 13 times 1 over 13, which gives me 1 over 169. Okay, so when choosing cards from a single fair deck without replacement, which means you draw a card and you just kind of put it aside and then you draw. So now you've only got 51 cards in your pile, and so then you draw your second card. Okay, so you've got 2 cards in your hand. So the probability of 2 5s is the probability of 5 on the first draw and 5 on the second draw, given that you already had a 5 on the first draw. So in our deck, we start off with 52 cards. There's 4 5s, right? The 5 of hearts, the 5 of diamonds, the 5 of clubs, and the 5 of spades. Okay, so we've drawn one card and it is a 5. So we no longer have 4 5s, we have 3 5s, and we no longer have 52 cards, we have 51. And so that turns out to be 12 over 2,652 is one, and that is 1 over 221. And versus or. So far we've been talking about and. And means both events occur together. So if we have events A and B, and is the overlap. Or means that at least one of the events occurs. It's okay if they both occur, but you want at least one of them. So that would look like the event A being colored in all the way and the event B being colored in all the way. And our little overlap there is still purple. It is included in our favorable outcomes and is picky or is not. All right, so your general addition rule is going to be that for any events A and B, the probability of A or B is going to be the probability of A, so the area of the pink circle, plus the probability of B, so the area of the blue circle. But we've added this little purple part, the part where they overlap, we added when we did the probability of A. Then we turned around and added with the probability of B. So we need to subtract it off once because it's been added twice. Okay, so when choosing a card from an ordinary deck, the probability of getting a 5 or a red card. All right, so we're going to need the probability of a 5 plus the probability of red minus the probability of 5 and red, because we have added the 5 of hearts and the 5 of diamonds twice. They get added here when we do the probability of 5, and they get added here where we do the probability of red. So we need to subtract them off once. So the probability of drawing a 5, there's 4 cards out of 52 that are 5s, plus the probability of drawing reds, there's 26 red cards, so 26 out of 52, minus the 2 of hearts and the 2 of diamonds, the 2 5s that are red. It's going to be 28 out of 52, which is 7/13. When choosing a card from an ordinary deck, the probability of getting a 5 or a 6. So here we're going to do the probability of getting a 5, which is 4 out of 52, plus the probability of getting a 6, which is 4 out of 52. And then we're going to subtract off the probability that a card is a 5 and a 6. Well, you've got one card in your hand. It can't be a 5 and a 6 at the same time. So that subtracts off 0 out of 52, so we get 8 out of 52, which is 2/13. All right, so these events here, being a 5 and a 6, those are mutually exclusive. A 5 can be a 5 of hearts, a 5 of diamonds, a 5 of spades, a 5 of clubs, but it can't be a 5 and a 6 at the same time. So those are called disjoint or mutually exclusive. Events that are disjoint, or another way of saying mutually exclusive, cannot happen together. So the probability of A and B is equal to 0. Okay, so there's no overlap. So if you were to use the general formula, you would always be subtracting off 0 when you did the probability of A and B. So you can simplify it and do the probability of A plus the probability of B. So when rolling an ordinary die, the probability of rolling a 4 or a 6, they cannot occur at the same time. Okay, we're talking a single roll. You've got a 1/6 chance of rolling a 4. You've got a 1/6 chance of rolling a 6. So you have a 2/6 chance of rolling either one of those, which is a third. Okay. Experimental or survey results are so important for you to be able to read and understand. So here we've got a two-way table or contingency table where we've got a group of people. There were 187 people, and some were males, some were females, some were college graduates, and some were not. Okay, so here we have 54 males who are college graduates. Here we have 31 males who are not college graduates, and they add up to be 85 males. We have 62 females who are college graduates and 40 females who are not college graduates, giving us a total of 102 females. We had 54 male college graduates and 62 female college graduates, which gave us 116 college graduates. We have 31 male not college graduates and 40 females who did not graduate from college. So we had 71 that had not graduated from college. If you add these row totals together, you get 187. If you add the columns together, you get 187. If you add the individual cells together, you get 187. All right, so the probability of being a randomly selected person, being male and a college graduate. Okay, so we want to look and see where those two things overlap. So those are our 54 males right here who graduated from college, and we would divide that by 187. Now, male or college graduate, you could kind of go about this a couple of ways. All right, you can do the total number of males plus the total number of college graduates minus the overlap, and you're going to get 147 over 187. Or you could do, okay, I'm going to do the number of males, 85, plus the number of any college graduates who haven't already been counted. So I've already counted the 54 of my 85. So I'm just going to do 85 plus 62, and you still get the same 147 out of 187. The probability of a randomly selected person being a male given they are a college graduate. Okay, so we're no longer looking at our whole sample. Okay, we're only looking at the 116 college graduates. So our denominator is now 116. How many of those were male? 54. So it's 54 out of 116. Note the difference between the probability of male and college graduate and male probability of male given college graduate is the denominator. With conditional probabilities, we restrict our group. So you need to pay attention to that. All right, so you have some problems to try on your own. Go ahead and finish those before you come to class. We will go over them. If you have any questions, please give me an email or run by my classroom. I am here to help you. Thank you for watching the video. I hope you have a great day, and I will see you soon.